Oh, yep, you're right. Minus 20. D, piece of cake. Row
I
operations
couldn't
for.
help it. Pringle and I were doing some stuff this morning. This stuff. And all of this is what I consider linear algebra matrix operations, just in a general sense. So you guys haven't taken linear algebra, right? So when you look at these equations, right, all they're doing in the linear algebra side is taking real stuff like this. I mean, if you take this and you make equations, you're using Kirchhoff's law, right? Or one of them. And you're just making a series of linear equations. And then you represent those equations in a matrix. That's where the weird stuff starts coming in, because the equal sign kind of disappears, but all the numbers stay there. They're kind of in position. So every one of those matrices represents some real thing, right? A scenario, like a circuit, or I don't know where this one come from.
This is a circuit.
Okay, it's a circuit.
It's that circuit right there.
Yeah, that's perfect. So you're adding up current, or you're adding up something, and you write it out, and you have 2, 2, 3. So you have 3 equations, 3 unknowns. Everyone's happy. I love writing in the matrix form because that's the way you enter it into your calculators and everything. It's and I also like it because I do this stuff in my head all the time, right? And the row operations, which if you get any book, and you guys should be thinking about this, because I have the cheat sheet books. I get the CRC math book, I get the Kreisig's, and I know give something in, because I always got to remember. I mean, there are things that are not obvious at times to me, so I'll go back and figure it out. But row operations are just this, do something up there, multiply it, whatever, so you can subtract it from the one below and make a zero come about, right? And you want the zeros because if you do it enough, you'll solve the equation, right? You'll solve for one of those parameters, right? And that's all you're trying to do is just solve the bloody thing. The whole intent here is to solve for the resistors or solve for the whatever, right? I mean, that's the intent. Or, anyway. And it doesn't matter what the equations are. That's the beauty of this. It could be a constitutive relation like I like, Hooke's law, stress is equal to something strain. That's great. Why not, right? Or it could be heat transfer. It could be some bloody Q dot equals whatever the heck I forgot all about it with H's and things, right? T's. It doesn't matter what they are. What matters is that you can write them out enough to make up that matrix. And if you have that 3 equations, 3 unknowns, you're good. Does that make sense? So try to keep it in mind that this is just a game. And all those math, when I took this stuff on the math side, they didn't show this. They just introduced equations, which really frustrates the hell out of every engineer. Because engineers like to know where it came from and what you're going to use it for and da-da-da. The other thing about this that's, you won't, how should I say this? It's really easy to say, sigma equals, modulus times strain. But in your head, then you got to start thinking, and I don't know if you did this or not. But
I haven't got that far. I showed them that equation. We're going to get farther.
The trouble is, it's in a direction, right? And you know that wood is not the same in each direction. Nobody splits wood against the grain, right? Why? Because it's not the same, right? So it's anisotropic and isotropic. So isotropic being the same and being not. So it's all screwed up anyway. The whole dang world is screwed up. In fact, every time you get a material, a piece of melamine, an extrusion, all the grains are smashed going that way. So even then that the modulus can be stiffer that way than transverse. So it's all screwed up. And then it's just a matter of how screwed up is it, doesn't matter, and do we have to worry about it? And if we do have to worry about it, how do we worry about it? And that's where this becomes so cool. And especially, of course, any advanced material, teaching composites, right? I mean, you literally want all the fibers in one direction on the top and bottom of a spar of a wing, because who cares if it's anywhere else, right? For the normal operation of the plane, that's all that matters. That means you can make a very light structure, purpose-built, nice, nice, nice. Well, that means that everything's screwed up. Not only is it anisotropic, it's inhomogeneous, right? Homogeneous would be the same content in each place, and inhomogeneous would be all screwed up. So how do you do that? Well, that's where no amount of statics and strengths and analytical stuff is going to help you. You have to go numerical, because you're doing element by element. You're going all over this stupid structure, and each of those elements is assigned some sort of modulus, right? A descriptor of how it responds to a load. Because all the numerical does is take all these loads and do a lowest energy manipulation, if you will, and come out with a shape that fits that load, right? That's all it does. So each element can be different. It doesn't matter. It'll do anything. These are powerful, powerful programs. I mean, Cosmos is cool. Of course, it'll give you crap the more crap you put in, but it makes pretty pictures. Okay, so the deal is, then you got to figure out where if it's an X direction, and okay, that's cool, right? X, and all of a sudden we have this. If you have an X, a Y, oops, a hat, and a Z, then you have this, right? I mean, the Y depends on the Y, right? Well, not really. See, I'm already lying. Because what happens when you pull something? Do all the dimensions stay the same except that one? No. What happens? Shrinks. It's like, oh, shit. So then you say, fine, I'm an engineer, I can do this. We subtract off stuff. What do we subtract off? Well, it's that Poisson stuff. So it's like a Poisson and a gamma, and that like a Y and a Poisson and a gamma in the Z. Only it gets, all of a sudden, things are getting really freaking messy. Because you have to do it down here, and, well, you know, we have 3 dimensions, so we might as well, right? See where we're going with this? All of a sudden, shit, here's a vector, here's a vector. Holy crap, there's a lot of stuff in there, though. And there's a lot of these. In fact, you can, at one level, you can make up, you know, I mean, you can, how shall I say this? You know this thing, stress? What am I using this for, this sigma? What kind of stress? Normal stress, because, Jesus, all of a sudden we have this tau, right? I mean, this gets messy, you know, and it's powerful. So all of a sudden, if you want to do it in this kind of matrix way, you can say, well, we'll do the sigma x, sigma y, sigma z, tau x y, tau x z, tau z y. There's a vector, right? And then equals on a whole bunch of stuff. And then you have the same thing, epsilon, 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 gamma, 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 right? And you have how many in there?
6 by 6.
6 by 6, so 36, these little buggers. And that's simple. Isn't it great? I can make it worse. Isn't it cool? So the highest I went in the grad school FEA side was this 81 element thingy from hell. And, you know, it's a 9 by, you get the idea. Why not? I mean, just because instead of x, you say sigma 1, 1, right? You can have fun with this. When you think of all these numerical programs like Cosmos out here and everything, this stuff, this, is what's stored in there. So when you say you have to choose, it's a steel, it's a, right, you have to choose this stuff, it picks this out. And then if you say it's a composite and it's anisotropic, you have to either find it or populate it. And sometimes, I don't know if our Cosmos does that. When I was doing the work at Wazoo on my PhD, we were deforming stuff, and that's a whole other game, right? When you're trying to like extrude or something like that, because you know it's going to change shape, so it's not elastic anymore. If it's not elastic anymore, gone. You have to have a whole nother stress, strain, and something in the middle, because it's not elastic, right? It's plastic, right? This stuff only works if you have a line, right? That's elastic. So if you have something like this, right, then it's more of a power law. It's like to the N or something, right? So it just looks different. But it's still that stuff in the middle of a constitutive relation that we generate. That's part of what I did, or the thing I did was for one material in one regime, I made one of these and we sold it to market analysis. That was, in a nutshell, who funded my doctorate, right? But all of this is intended to allow us to predict what the deformation is from some sort of load, knowing something about the material and how it behaves. So, you know, in a way, it's like, my message is, get enough of the linear algebra down to handle these stupid matrices, and then try to figure out how we get these series of equations from whatever it's coming from, circuits, constitutive, you name it, and how that is represented in that linear algebra, the matrix, if you will, and then what you get out of it, and all of those other, you'll talk about it later, all the constraints on that kind of stuff. Did I do enough damage now? Okay, thank you.
You horrify us?
No, so we're just doing the baby steps to get up to what Dr. J was talking about. And that's what we're working through today, is those baby steps. But that's kind of where we're going to end up. And, it's so that you're aware that that's what our FEA software is doing. Don't worry, we're not going to do a 9x9. We're not doing any of that.
So when he was saying he came up with the matrix for that place, for that company he was talking about his PhD, is that the solver then that we were talking
No,
about?
that's not the solver, but that's what the solver uses when it's manipulating each one of the nodes.
Okay.
And that comes from testing, tensile testing and various other things to get, figure out what that's going to be in the various different directions. Because, wood, like you said, or started out with, we know that's not homogeneous. And so you're going to test it in at least 3 directions, and you're going to get different values for each one because of the grain structure. So, anyway, so I know that this seems kind of a little out of context, or you're just sort of following along with these numbers, but the idea being that kind of once you get a sense of what the procedure is and how to do this, then when we, relate it, we can relate it back, and it'll hopefully make a little more sense. So, but we'll continue on with our baby steps and our little example here. So let's see, so we did the math, and I didn't write it out in the equation form, and just left it in the matrix form here. But, so our next step would be to do what on this matrix, if we're continuing on with our Gaussian elimination? What would the next step be?
So next two. Is that the next one?
Well, so we start out with the top equation, right? We create a pivot, and then we want to eliminate the first term. So then when we go to the next one, we want to create the second term as the pivot and eliminate the next row, or the next, or that column, right, out of the other rows. But as you can see, that term is 0. So there's nothing there. So we can't use that as the pivot, right? So all we have to do then is we're going to rearrange, rearrange our equations. So we'll say this one is 0, 10, 25, 90, 20. And we'll just move all our zeros to the bottom, right? So now we have a term that we can use for the pivot to subtract from this next equation, right? So let's see, we want to subtract, so if I say this is my pivot, right? I want to eliminate so how are we going to do that?